Okay, so welcome to lecture 14 already. Starting with the summary of week 7. So we continued the Landau-Ginzburg recipe of how phenomenologically derive an effective Hamiltonian, where we added to the previous arguments to have locality and uniformity, analyticity, and symmetries, where we had previously talked about rotational symmetry. We added isotropy, which led us to realize that only quadratics of the divergence are lowest order terms that we can respect under this symmetry, and then higher order would be, for example, m squared. Like there are other higher orders that we can put together, but we should have to make sure that they're isotropic. And last, there was the concept of stability, which gave us insight into the signs of prefactors. And with all of that together, we found the Landau-Ginzburg Hamiltonian for a magnetic system, where we have the constant term. It's typically neglected. And then we're integrating over space. And because of the symmetries, we own the lowest order term is an m squared. We include a first higher order term, which is m to the 4. The spatial coupling comes in due to the divergence, which is squared to respect isotropy. We could add more higher order terms. What we do put in is the magnetic field. This came up from the phenomenological rules of how to set up a Hamiltonian, but we also did the derivation of the Landau-Ginzburg Hamiltonian for an Ising model by really doing the coarse graining. And the first start here was to coarse grain by we needed the Hubbard-Stratonovich transformation to write our spin systems in terms of field variables, and then turns to the Fourier space to then look at long wavelength. Perturbations, and then really arrived also with this coarse graining approach really at exactly this Hamiltonian. The way to actually deal with these Hamiltonians, again, this is very hard because we have to sum over all possible states. And now the trick is to say, like, look, if I take the Boltzmann factor of this effective Hamiltonian, the contribution is highest from what is maximizing without the minus, minimizing without the extremizing this functional. And so I will look for the uniform field that is extremizing this functional, and then try to look at the dynamics of this specific system. And this is the so-called saddle point approximation, or Gaussian approximation. So we search, oops, for a uniform field which minimizes the Hamiltonian and thus extremizes minus beta h. And this is then in the saddle point approximation, we showed that for the isomodel, we recover mean field theory. And then we talked about breaking of symmetries. So we talked about continuous symmetry breaking. This is something that we can have only in 2 dimensions or higher, because there the Hamiltonian has, first of all, a rotational symmetry that can be broken. And so this is spontaneously broken by a rotation that is slowly varying in space, of the kind Rx, Mx. And these rotations, they have a name. They're called Goldstone modes. And their energy cost is kq squared, with k proportional to t. So the cost means t being the reduced temperature, the cost is 0 at the critical point. So it's a very low cost. So as soon as I put thermal energy into system, these these modes can be excited and break the long range order. In lower than 2 dimensions, we can't break a continuous symmetry, but we can break a discrete symmetry. So this is, for example, for d equal 1. And so what we can have here is we can have domain walls, which just means that, we have plus signs and then eventually minus signs, spins being aligned. And so for the 1-dimensional system, we were also able to really calculate the energetic cost of such a domain wall, to find that we here have better free energy of such a wall is minus 2/3 average magnetization width of the wall and cross-sectional surface area of the wall. And again, we see that this term is proportional to the reduced temperature. So also the cost of domain walls is 0 at the critical point. And last, we started talking about the fluctuations around the settle point. And so here the answers was to write down the magnetization as the average magnetization, which without loss of generality, we have point into the x1 direction, plus fluctuations around them. And here we distinguish longitudinal fluctuations that are aligned in the direction of the average magnetization, and all the transversal fluctuations that are in all perpendicular dimensions. And when putting these answers, looking at the fluctuations into our Hamiltonian for the Ising model, we could rearrange these to find that we have constant terms contributing here, which are not meaningful, but then the contribution is of the modes comes in as k over 2 sorry, we want to have the fluctuations here squared, oops, plus and similarly for the transversal mode, we can really write them as, oh, sorry, transversal. What looks like a Hookean spring. Yeah, sorry, just checking that all the brackets are in place. So these would be the transversal, the longitudinal modes, the longitudinal fluctuations. And these are the transversal fluctuations. And we can really see that the energetic cost really looks like a Hookean spring, where the stiffness of the spin is given by k over psi l. And what was interesting to really look at the values of these stiffnesses, so k over psi l, is it squared? Is it squared? Should be, right? Is proportional to t, both for t smaller and bigger and smaller than the critical point for the longitudinal modes, but for the transversal modes, we find that the stiffnesses vanishes below the critical temperature. And so what we discover here is these are the Goldstone modes. So the continuous breaking of symmetry. Yes, and there was a square. Okay, and so today we're going to continue on fluctuations and then talk about the lower critical dimension in this context. Do you still remember what the lower critical dimension was? What was the definition? Yes.
Yeah, it's the dimension where, like, at a certain point, if you lower the dimensions, you don't get any phase transitions anymore. So
exactly, yeah. So it's the lowest dimension at which below which we won't see any phase transitions anymore. And so therefore, like, it's a it's a hallmark for the different models to at which level we would see phase transitions. And so we're here looking into the role of fluctuations, because the fluctuations are typically governing if and where, at which dimension we observe phase transitions. Okay, so if we now continue, looking at fluctuations around the saddle point. So we derived last week that we can write the Hamiltonian in this fashion, and this looks like a stiffness if mapped to the Hamiltonian. And I also told you that this length scale squared that's popping up here, we can interpret this as a correlation length of the longitudinal and transversal fluctuations. But this is indeed the case. This I didn't show you yet. And so this is what we dig in now. And so for that, we again consider Fourier modes, phi L Q and phi T Q, by defining them as 1 over the volume of the space, phi L Q into IQ X. And so putting this answers into our Hamiltonian, due to the derivative squareds, we get a Q squared term for both of these first terms, such that we can write our Hamiltonian or the probability distribution, which is then the e to the power of the Boltzmann factor of the Hamiltonian as that's not a beta, but a p. So the probability distribution, which now depends on the Fourier modes of the transversal and the longitudinal modes, where I'm neglecting this constant prefactor, is then the sum becomes a product, because I have now put this into an exponent to have the probability. And so we get the k over 2, and then a q squared minus plus psi l squared times, phi lq squared times the same structure for the transversal modes. And this is really where the going into Fourier space unfolds its power, because we can readily read off the correlation functions of these variables. Because what we see here is that indeed, by going to Fourier modes, our derivatives went away, and I see that there's only a quadratic dependence of the longitudinal and the transversal fluctuation, each independent. So what we have here are like purely Gaussian variables, of which I know my my correlations. So the modes are independent Gaussian of and it's mean 0. And the 2-point correlation. Then so phi alpha q phi beta q, just to write it down in general term, because alpha and beta could now be different directions of the transversal the longitudinal and the transversal modes. So I only get a contribution if those two modes directions are aligned, and I also only get this prime q prime, and then the magnitude is k times q squared over psi alpha minus 2. And this is really powerful because these fluctuations I can now measure really in scattering experiments. And so what I gain is, so I can measure these in scattering experiments, these correlations, and they give me direct access of what we're gonna see the correlation lengths of the different modes. Just to give some more details and connect to experiments here. So the way it works is now we can measure so for example, we can use neutrons which have a magnetic moment but are uncharged to probe the magnetization. And I can use spin polarized neutrons to probe longitudinal and transverse modes of fluctuations separately. And so what we find is that the scattering intensity, it's usually abbreviated with an SQ of the wave vector, is then proportional to actually the phi alpha. Right. Let me just chat a little bit. The square of the modes. And so what is really cool here is now that we can, so we're building all this theoretical framework, right? But we here, our aim when building a theoretical framework should always be to also derive expressions for experimentally observable properties. And that's why we care about these fluctuations, right? So we want to measure, obviously, the phase transition, and we want to have not just derive any observables that in principle could be measures, but we really need to, and this is something that you know, if you're very interested in doing theoretical physics, an aspect that you should also invest time into is like knowing about the limitations that you have in the experiments in your field of choice of the science that you do, because in the end, like your theoretical predictions, they can inspire, like, you know, you can have just ideas, you can put down mechanistic models to inspire an idea, like, you know, how would it be if this and this work together? But your ideas will only flourish if you can convince someone to actually see that this is that whatever your idea has is really what's acting in a physical system, right? And I think this is what really makes physics, that we live from this idea that we make hypotheses and make predictions, and then we test them in experiments, and then go back and refine, right? So, you know, we're going through a cycle. I think actually advanced statistical physics is a nice example of going back over the last 100 years, starting from the Ising model of like how, you know, theoretical ideas being put forward, they didn't match experimental observations or numerical observations. And, you know, there was a refinement on continuous refinement on the theoretical methods to actually describe the system in a successful manner. And so that's why we do care so much about these fluctuations, because they are something that you can measure, even though, but, you know, with a lot of work, like first of all, having neutron source and so on. And so then the scattering intensity will directly give you access to these correlation length, because this we saw was just, sorry, I need to have an alpha index here, so I can have an alpha index down here. And this is what's called the so-called Lorentzian rule. And this is the correlation length. To the direction alpha. Oops. And so the way experimental observations look like is that this Lorentzian rule is indeed an excellent fit to the scatter line shapes. So but only away from the critical point. So let me now plot this S of Q as a function of the wavelengths, the wave vector we're probing. We observe this for below the critical point, where the turning point, which is very hard to see in my drawing. What happened? Then here defines the inverse of the correlation length. And so from this, we really see that this is really a correlation length. I'm going to give you a mathematical derivation of that too. However, what happens at the critical point looks more like that. So where we have a 1 over q square dependence. And indeed, the critical point, this scales more like q2 minus eta, for eta bigger than 0, but very small. So this variation, the deviation from the factor 2 is hard to distinguish in experiments. So we get this, yeah, not nicely drawn q squared dependence. Think of it. I can try to do a better job. Okay, whatever. So that would be T0. How can we see this? So now we want to really calculate the correlation functions as a function of the dimensions in the system. And so remember the definition of connected correlation. The corrected correlation function was G, well, we had gammas there too. Here I'm using the G just to make you aware, and there are two indices for the two different directions, because now we're in multi-dimensional space, so not in one dimensions as we had it so far. So this is now a vectorial order parameter. Valued at x and x prime, and so that's m alpha of x minus the average reduction of alpha beta x minus the average. And so this is exactly, if you allow me to scroll back to the answers of here, the answers of my fluctuation ansatz. So if I look at the difference between the magnetization and its average magnetization, the difference is just given by the fluctuations. So this is exactly then just looking at the fluctuations into the chosen directions. In this, we read off from going into Fourier space as being one. We now go to Fourier space. These were defined as Q prime, e to the I Q x, e to the I Q prime x prime, and then the Fourier transport Q prime. And this we knew is just delta alpha beta delta Q prime over K Q squared plus Xi alpha minus 2. And so that's then just minus delta alpha beta over K. And I'm defining this as the d-dimensional function that now depends only on the spatial difference, which you see popping up here, right? And the correlation length with ID. Now just writing it as a difference as minus eta IQX Q squared plus Xi minus 2. And so now this integral, now going from Fourier space back to real space, I can solve now respecting the limits. And so what I have to pay attention to is if my integral, if I'm in x smaller than this correlation length or x bigger than the correlation length. So to find that I have x minus, d over 2 minus d times the structure factor, which is a constant, and here Xi 3 minus d over 2 minus d, same factor, xd minus 1. But most importantly, ta-da, I find for x, sorry, the other way around. X bigger than the correlation length, I indeed find an exponential decay as I expect for the definition of a correlation length. That the correlation length is governing the spatial scale over which correlations decay. Which tells me that really indeed the Xi is a correlation length. So if we plot now this function ID x as a function of x, we first have a power law kind of decay until Xi, and then an exponentially loops dominated decay after that. So this is really now the justification for Xi being identified as correlation length. Yes. Yeah.
What's the is this an S in front of the D, and what's the S, or what's
this is the structure factor. Like it's a constant that I don't go into details here now.
Oh, okay, it's just something. Okay.
Yeah, it's just like, let me abbreviate this jumble that comes there,
Oh,
so that we're not looking at prefactors that are important, but focus on the dependence on X, which I have spelled here, and give you the terms where the dimensional factor come in.
Yep.
And what you can also take from this expression is now that there are dimensional, like the dimension pops up as a factor, and we can already see that something funny must happen at d equal 2, right? Because then all of a sudden I here have x2 minus 2, and something looks different here, because then all of a sudden I wouldn't have a decay, but I would have a constant. And so we find that specific dimensions have a strong impact on the functional dependence of the role of fluctuations. And so as I outlined before, we are interested in identifying these lower critical dimensions. As we go on, I think end of this week, we also talk about upper critical dimensions. So they're actually 2 boundaries to consider. But for now, we're interested in the lower critical dimension as the dimension that tells us for specific universality class above which dimension I should expect phase transitions to happen. And so this is now the second topic of today, to look into the lower critical dimension. And so the question is, what is the effect of fluctuations on the ordered phase? With ordered phase, here being the mean field theory. Mean field theory being here synonymous as the saddle point approximation, right? Because we saw if we start with the field theoretic ansatz and look for the saddle point, the uniform field that extremizes our Hamiltonian, we recover mean field theory. And so both the ad hoc derivation and the field theoretic derivation of mean field theory give the same result. We do know a little bit already of what we would expect as a role of fluctuations, because we talked about symmetry breaking, right? So we've seen that for D2 or bigger, there are Goldstone modes, which are nothing else but really fluctuations, long wavelength fluctuations, or long wavelength variations, continuous variations. Let me put this in. It's a continuous thing breaking. That are easily excited by thermal fluctuations. And so can we cast now these Goldstone modes in this framework of fluctuations? Remember when we talked about the 2 types of continuous symmetry breaking last week, the 2 types of symmetry breaking, I gave you a derivation of the energy for the domain boundary. But I only sort of said like, yeah, and the Goldstone mode, they have their energy scales with Q squared. Because at the time we didn't have the tools yet to really think about like, what is the energetic cost? And so this is what we can now do, given that we really calculated the Hamiltonian for the fluctuations, and we can look into that. Just to add, also consider that in d equal 2, now we consider d equal 2 in arbitrary spatial dimensions. This also exists, and that's, for example, as superfluid, superconductor fluid. So we're looking at really now the Goldstone modes variation embedded in any dimension. And so now what this means is that actually our fluctuations that, where are they? We abbreviated just by, by any, just a factor varying an E, writing down both dimensions. What we can now do is to say, okay, so we consider now transversal fluctuations in spanning 2 dimensions, and we write them as a constant amplitude and an angular variation, which is exactly what we think about when we have these transversal fluctuations. So it is useful to now write the order parameter itself as complex variable in polar coordinates. So we're lumping both fluctuations together to now write mx as psi x, where I have a constant, I will consider a constant amplitude and an angular variation. And then I can now do the same kind of math as we did for the fluctuations. And we here focus on the transverse fluctuations. T. And we take the amplitude to be uniform. That's the field idea again. And we're looking for the distribution for the transverse fluctuations. Okay, so remember we had this probability function just written down as a function of the fluctuations, now focusing on the transversal ones, which I write as psi e to the theta. We have this exponential dependence of d dx k over 2 pi t squared plus t plus 4u 2 t squared. Okay. So now making this ensemble of constant amplitude and spatially varying polar phase, the square, this is just the amplitude, right? So this whole term is actually just constant. And so the only way where the polar phase comes in, which is spatially depending on x, we're thinking about, this kind of a rotation transversal to the average magnetization, that here we get a spatial derivative of the theta term. And so this is where the theta dependence prevails. And so we can write this as minus k over 2 ddx gradient theta, where we here, this is a different k now compared to the one above, because we here really subsummed all terms of the psi x constant. So these terms and so on. Okay, so we really only have a quadratic dependence on the spatial derivative of this polar phase. And yay, that we know how to deal with, right? And so the way to deal with this, to understand now the correlations of these polar angles, is again to go into Fourier space. So if you go into Fourier space, we already know that what we find is that now the thetas become, again, the Gaussian independent variable. Because, sorry, that's not in vector. There we go. Summing over all q's. Because of the derivative, we get a q squared. And we get a theta q. Where this actually, oops. This here actually means that this is the complex conjugate, the product of the theta and its complex conjugate, which is nothing else than times minus q, which is just the same as looking at the real value plus the imaginary part squared. And so we see that indeed we came back to the same functional dependence of theta being independent Gaussian random variables with zero mean, of which we know the correlations. Yeah. So we then know that theta q prime is delta q prime over now k bar q squared as before. And so now knowing this, we can go back to the correlation in real space. So we know that the average, the mean is zero. So the random variable was zero mean. And the correlations are theta x prime and 1 over v summing over q prime e to the I q x to the I q prime x prime, and then putting in the delta q k over q squared, we find that this is just 1 over v, sum over q is left, e to the I q x minus x prime, and k q squared. This is still a sum of wave modes, so we want to take the continuum limit. by sending the volume to infinity, such that the sum over wave modes then becomes an integral over the modes within the Bragg zone, and hence we then can write the spatial correlation as integral, the v's cancel, d dx, d dq, 2 pi over d e to the I q square. And so this integral I'm going to define again as a function CD. The correlation is depending on the difference over k bar. Sorry, bar. Yeah. Bar, yeah. Okay. And so now we can learn about the spatial correlations of our polar variable by evaluating this integral. And you see the integral does depend on the dimension. And so the dimension will come actually into play when we evaluate. Okay, oops. So we now need to determine this correlation function, which now I write only to be dependent on the difference vector. Okay, and so I'm pretty sure we can just go in and force evaluate this integral, but I would choose here to take a different route because you're a physicist, right? You've seen this integral before. Do you know which theory class you had this? It goes back quite a while, actually. Think of
I mean, okay, it looks like the Klein-Gordon thing without a mass. So it's like a Yukawa potential, but like
no. Okay, go back to bachelor's, not master's level.
Oh yeah.
This is just the electrostatics. This is just the Coulomb potential.
Yeah, Yukawa potential without mass is a Coulomb potential.
Yeah, but I wanted to like that. The simple expression that you feel like no. Yeah. So exactly. So it's just the Coulomb potential. Yeah. So it's just electrostatics that we have here. That small difference, d dimension. So we have this dimensional integral that we now have to distinguish how it works out in different dimensions. And so why is it useful to draw this analogy? Because obviously, if you think about the Coulomb potential in 1D, in 2D, and in 3D, you would expect a different, your physical intuition already tells you that the functional dependence of this potential will be different, right? If I change the dimension. Okay, so we could try directly. So CD X is in potential. It's not actually surprising that we do this. So you will find there's just a limited amount of math that we have available. So it's typically that we simplify our physical problems to the ones where we have the math. so I still remember, like, I did, as a master's student, I went to Manchester for a year, and it was like a taught master. So I was taking classes, including, for example, advanced statistical physics, but at the same time had a project. And so I was lucky in a sense that, they just assigned you for the project, they just assign you a professor. And so the professor I got assigned was Alan Bray, who was a hero in spin glasses, big person in the 90s. But at the time had, like, I think one other PhD student and his master student. And so he gave me this wonderful project, which it's so cute in the end. So he said, like, oh, for master project, like, numerical work that's way too hard. Like, you need to learn to code, and, we won't do this. Like, this is too hard for you. So I will give you an analytical project. Which is, like, in my experience, it's the opposite. It's so rare that you find an analytical project where you can really solve a novel physical challenge by pen and paper. And it's much easier to just dream up a project which you can solve numerically. But, he came from a different era. He was like, no, you get an analytical project. And so he gave me an analytical project, which was actually based on stochastic processes, which I should, again, encourage you strongly to take the class by Ulrich Gerland in the summer term. And then eventually, I succeeded, I solved it. I mean, he basically knew that it was solvable. Like, it was just, I guess he would have, just taken him to sit down for 2 days and actually solve it, because he knew it would solve it. Anyway, and I solved it, and I came up that, I was so proud. I was like, I found it, like, it's this and this function. I don't remember which function it was. And he was like, yeah, I thought of that. And I was like, gosh, how could he know that, I've never heard of that function. Like, why would it be that function? And it took me a while to realize that it was just the most general function that we gave a name to. So, which is, it's enough to be, like, tabulated, and people, thought about it enough that we have identities and limiting cases and these kind of things. But basically, I mean, we can deal with polynomials. And then as soon as we start talking about Bessel functions, we're in that game, right? So we just found a function that's coming up repeatedly where we can still say something about limiting cases. But I mean, honestly, the only thing that we can do is just put it in a computer and plot it, right? But we cared about it too much because it comes up in lots of cases. And so that's why we gave it a name, and that's the Bessel function. And there's just a limited amount of names that we gave for functions before we gave up, because we couldn't derive any, like, limiting cases or identities of how you could transform these functions and so on. And so it's really that, like, there's this book, like, or you can look it up in Wolfram Alpha. You just have this limited amount of functions, and by no surprise, every time you are actually able to solve it, you will end up having one of the functions. If you're lucky, it turns out that it's the Bessel function. And if you're less unlucky, you have, like, less lucky, you have, like, this most general function. I should look it up.
The hypergeometric.
Yeah, it was the hypergeometric. Thank you. It's just the most general, yeah. And it has sadly also the least amount of identities, but it had enough identities for my project to be solved, which is really wonderful. And I mean, just to give more credit to Alan Bray, it's so funny. Like, he then said, okay, you solved it. So now you go and write a paper. I was like, okay, sure, can write a paper. And so he also taught me how to write a paper. And then he was so laid back. He's like, okay, Karen, so how about, so I was like, okay, so how about the authorship? Like, and he's like, oh, I don't care. What do you think? And then I was like, well, it was your idea, and you basically had it all in mind. So I feel like you should go first. And he's like, sure. So it turns out that my first ever publication is actually last author publication, which then took me another, I don't know, more than 10 years of a career to arrive at. Because typically, like, if you're the person doing the work, the person who had the idea goes last, and you're doing the work goes as the first author. But he just so doesn't care. And so he had him go first. And it's true, you can look it up. It's under my maiden name, Karen Winkler. But it was funny. It just, yeah, he just he just didn't care in a good way, right? He cared about the project, but he didn't care about this. So there's really something in, like physics-wise that, you know, you do end up finding this, you know, it's just what we can solve. And it will hit you in classes a lot more, right? Obviously, because we tend to show you examples that we can solve, but it will also hit you when you do your own research project. It's the same thing. Okay, so that's the charge at the origin and the dimensions. Okay, so we know this about the Coulomb potential, right? So we can use that this, which if we act this on our integral, we get a q squared down. Get d to the q 2 pi d, I'm copying this down. And then I get q squared over q squared e to I. That's just the delta functional and d dimensions, note. So we know the result in 3 dimensions, but we really want this now to be d-dimensional. We know in d3. So we integrate over all space, left and right. So if we do this on the left, ddx of cd of x. On the right hand side, we have the delta functional, the dimensions. We know that this integral on the right hand side should be 1. And on the left hand side, we apply Gauss's theorem to show that is just a surface integral over just now the divergence cdx. And because of the spherical symmetry of the system, we know that this divergence can only be depending on R of the spherical symmetry. We know that this needs to be dCd dr in either direction. And so what's actually lacking then is what is now the surface integral in d dimensions. So we need the surface area of a d-dimensional unit sphere. And here, this is 2p d over 2 with, so for d equal 1, we had gamma a half. It's, for example, square root of pi. And talking about functions, gamma function, right? Gamma functions, we know identities. So we know that gamma of x plus 1 is x of gamma of x. So with that, we can also, for example, get d equal 3, because that would be gamma of 3 over 2, which we can write as 1 over a half. We know gamma of a half, which is square root of pi. So that's just a half times square root of pi. And so, for example, then we have S3 being 4 pi. So that also makes sense, right? That's what you've been what you know of. Okay, so then if we plug this back in to this expression, so we have the one on the left hand side, which are moving on the right hand side, which are moving to the left hand side. And that's then S D R D minus 1 D C D D R, which we can solve for rearrange to be 1 over S D R D minus 1. And integrate this to find CD of R is R 2 minus D, 2 minus D, sorry, SD, plus C naught, a constant of integration. Okay, and now the SD that we had before, which I told you is just a factor ignored, because it didn't have any a constant, which it doesn't have any x dependence. And this is your SD that we found before as well. And so now we can look at the limiting behavior at large distances. So for large distances, R to infinity, we find or x to infinity. So that this is a constant for d bigger than 2. It's R to d, should have made more space, for d smaller than 2. And I get a marginal behavior at d equal to. Okay, so here we are. So what does this mean now? Okay, so this is this was the correlation of my angular variation. And so we find that this correlation grows with R large at infinite for d equal 2 or d smaller than 2. So that means that these correlations are unbound. And that means that I lose any order that I have in the systems, because these fluctuations will give rise to correlations that are unbound. And it's different only for d bigger than 2. That these will be bound constant, there will be constant, and that order should be retained. Yeah.
How does d equal to imply this limit?
Yeah, so here we have to be more careful in evaluating this integral, because we're running into this not being well defined, right? You see that here we have that we have to there's special care of d equal 2 that I'm shoving under the rock. Okay, but what we see for d equal 2 is, so the variance of the base wasn't definitely but the distance. That's finite for d larger than 2. Now, but since this cannot be, because phase is bounded by 2 pi, this divergence means that order is lost. Maybe long-ranged order is destroyed by the thermal excitation of the Goldstein modes. for d smaller than 2. So what we here find is now that we don't expect from this argument any order for d smaller than 2, but also for d equal to, right? So now here, our lower critical dimension, below which we don't expect any order, is d equal to, because of the Goldstone modes. Yes, question.
I mean, so how I remember it was that the correlation can be written like as e to the minus of r over the correlation length. So if the correlation grows with the distance, then like I somehow interpret it as a negative correlation length. Like, I mean, it's not even exponential here, so I'm kind of confused how this interpretation comes to place.
So the when we say that we're looking at the correlation, then this is an ad hoc concept that we're putting in. So we define the correlation lengths as a correlation speed fluctuations decaying with an exponential function. But if we here now really calculate bottom up, what are the correlations of these angular orientations? We just happen to arrive at a result that doesn't obey an exponential decay. But that's kind of that sort of comes out of the physical system. In our view of, you know, if I have a correlation length, it's defined as that this should obey an exponential function that's decaying. That's just not adequate here. So this is what we learn. And here we're really looking now at the correlations of these angular momentums, right? And we don't actually expect there to be a correlation length, which you can already see by comparing this setup of how the fluctuations are governed just in Fourier space compared to the fluctuations governed by when we looked at the here is the exponential function here, right? Well, yeah, what about here, right? So here you have the correlation length, and it's a finite value that we know, but we also know that this correlation length, so we have this correlation length, and indeed it pops out to have this exponential decay, right? And so our ad hoc assumption that we define correlation lengths as 1 over e to the x over this correlation length is something that we find here, and so we can really identify this length scale of the correlation lengths for these fluctuations in general. But here we're looking at a special case now, namely by asking really what are the dynamics of the Goldstone modes, right? Basically, and the Goldstone modes being now a superposition of 2 transversal modes, right? Because we wrote, okay, so
transversal and longitudinal,
no, it's just a transversal, right? Oh. So the longitudinal would be along the axis. So longitudinal is like speed of sound. It's like variations like that. And transversal is in d dimensions.
Oh, okay.
And so here in this answers before, we had looked at the individual transverse fluctuations. Where is it? Here, right? So we just wrote it as a shorthand, but this is actually always the, all individual transversal modes, right? And now we pick 2 of those and superpose them in saying, okay, I think you have a constant magnetism, like a constant amplitude, but you're rotating in space.
Sure.
And then this is my answer for saying, what's the background of the superposition? And if I take this superposition of 2 transversal modes, then I arrive at a setup where I don't expect there to be really a finite correlation. Thanks.
Okay. And that's what also we like commented on, like saying those are independent modes.
Yes.
Okay, I see.
And then I arrive at this result bottom up, which tells me, okay, I can't describe the system as correlation length, but we're also looking at an angular coordinate, right? It's not like we're looking at the magnetization and how the magnetization decays, but we're looking at how angles are correlated. And if you would have them correlated, we'd expect, the correlation lengths to be, for example, constant, right? But if it grows, this is unphysical behavior, and it tells us that something is going wrong. And I wouldn't expect phase transitions at d equal 2 or lower. And note, and so this is what we would expect here. Sorry, I don't want this one. So this is what we would expect from looking at Goldstone modes in the context of the mean field theory, right? But we already know that this is one theoretic framework which tells us a lot about phase transitions, but it always has its limitations. And so to jump ahead a few lectures down the road, indeed, if I actually careful treatment with other methods actually shows that I can have a phase transition for a 2D superfluid. So saying that this lower critical dimension of d equal 2 comes from the mean field result, but in reality, we find that 2D superfluids, it should actually be d equal 1, right? And also note for d equal 1, which is the case that we can't look at when we considered Goldstone modes. We only have discrete symmetry breaking there, and there are no Goldstone modes. But long-range order is destroyed is also destroyed by domain boundaries. Due to okay. In this, there's a general result, generalization on the definition of at which dimension you would expect symmetry breaking to take place or not, which goes back to the Mermin-Wagner theorem, which also you as TU students should know, because Wagner was he was a statistical physicist at the LMU, retired in like 2003 or something. So I still had classes with him, which maybe makes me old, but anyway. So so there's the Mermin-Wagner theorem. Doesn't follow from field theory, but sort of goes beyond. But I'd like to mention it here just because it concludes this topic. And it states that there is no spontaneous breaking of a continuous symmetry in systems with short range interactions in dimensions d smaller equal to. So this is in line with the upcoming result that we do see phase transitions in the 2D superfluid, in fact, which we can't recover from the theoretic approach. So this concludes the theoretical insight. I will now start to give you a short reminder on these Gaussian integrals that we're going to use for the upper critical dimension on Friday. So this is just mathematical prerequisites that we need. So in 1D, we consider the following integral, minus infinity to infinity, d phi of e to the k squared phi squared plus h phi. So Gaussian integral is non-zero mean. The way to solve this integral is to shift, to do a variable shift, which is by introducing new variable psi, which we define as k over 2 phi, and that allows me to shift this this constant term in here to make it quadratic. Integration, change of variable factor coming in, and then writing this is minus k over 2 phi. Sorry, no, psi. Sorry for that. Psi plus h squared. And we have k over 2 h squared left. And then this factor I can move front. It's a constant. Doesn't depend on psi. And I'm back on here having a nice Gaussian integral that I know the result of. So this is then 2 pi over k e to the k over 2 h squared. So that's for one dimension, but you saw that we really care about tackling different dimensions. So if we go now for n dimensions, this Jn is minus infinity to plus infinity. And here we would then have shorthand for all the different dimensions we need to integrate over. And to deal with this, what we're going to do is we reduce this product to n one-dimensional Gaussian integrals that we know how to deal with by dealing with this interaction matrix, right? So the way we can do this is to take any of this interaction matrix and diagonalize it, and then assume that the K is symmetric. We get the eigenvalues, and then we can diagonalize it in terms of the eigenvector. And then we can decouple the different integrals phi I and phi j into n one-dimensional Gaussian integrals. So the idea is to reduce to a product of n and k being symmetric means that the interaction of I with j is the same as the interaction of j with I. So we get the eigenvalues that are real Q, and we diagonalize eigenvectors Q hat, such that K acting on Q hat gives us QQ, the diagonal identity matrix with the eigenvalues. And so then I can represent the phi I in terms of eigenvectors Q hat, phi I. And so I think I'm gonna stop here. This is a recipe for next week. And then we go ahead because I would like to use the last 3 minutes to make you aware that the evaluation of the class started today. So you should have gotten an individual email with an individual link to provide evaluations. And I would really strongly encourage you to give evaluation. This is where you as students take power because you provide your feedback. And the idea of this feedback being asked for in December is that I can make use of that feedback, may it be constructive, may it be like also just saying like these things work well for the part after Christmas, but it's actually much more. So you give valuable feedback to me in my teaching, so I can improve this class. And when I, after Christmas or as we go forward, because I suppose I will teach it quite a number of times, but it's also your power to make political statements. Because I know that, or I'm aware that there's different styles of teachings and different amounts of materials being provided. Let's talk about recordings or making lecture notes available. This is your moment to provide this feedback. You provide it in written form. I read a paper, and trust me, I will make sure that we'll use this in discussions, saying like, but this is what my students said. This is what they really enjoy. This is what they value, and that's why we should make an effort to provide this. And for example, in my opinion, offer hybrid teaching, make recordings available, because in my opinion, you know best how you learn, and there's no way that I should tell you how you should have your best learning experience. And so I should try to cater the full breadth of how people enjoy learning, so that everyone can pick and make themselves happy. That's why I really encourage you to provide this feedback, which is valuable for me, but beyond also for how we organize as the Department of Physics, our physics teaching in future. Thank you.